Hello, and welcome to this video on the topic of moments, levers and gears. Most of us know what levers and gears are, but fewer of us know exactly how they work. Both devices are based on the confusingly named idea of the moment. The moment of a force is the turning effect it has on an object about a pivot. A pivot is just a point about which the object can rotate. Let's say you're trying to push open a door. Its hinges from the point about which it can rotate. We know that if we exert a force on the door close to its pivot, it'll be quite difficult to open, but if we exert the same force further from the pivot, say here, then the door will be easier to open. As we apply the force further from the pivot, the turning effect or moment exerted by it increases. In the same way, we know that it can be really difficult to tighten or loosen a nut with our bare hands. By using a spanner, however, we can increase the moment of the force which we apply about the nut. Again, increasing the distance from the pivot at which the force is applied increases the moment or turning effect of the force about the pivot. The equation for the moment of a force looks like this. M equals F times D, where M is the moment of the force in Newton meters, F is the force in newtons, and D is the perpendicular distance from the pivot to the line of action of the force in meters. Remember that if two things are perpendicular, that just means that they're at right angles to one another. Let's have a look through example 1 now to see how to use this equation. Here, we're looking for the magnitude or size and the direction of the moment produced, so let's give it a go. We can see that the force is 150 newtons and the perpendicular distance from the line of action of this force, which is represented by this dotted line to the pivot here, is 10 centimeters or 0.1 meters. To work out the magnitude or size of the moment, we use the equation M equals Fd and sub in 150 times 0.1 with d in meters, which gives 15 Newton meters. Next, the direction of a moment can be either clockwise or anti-clockwise. Here, because the force is pushing down to the right of the nut, it's going to cause it to rotate in this direction, which is clockwise. Why don't you pause the video now and have a quick go at example 2. Hopefully you'll see that this is actually a bit of a trick question, because the perpendicular distance from the line of action of the force to the pivot is 0. In other words, the line of action of the force passes straight through the pivot. This is a special case in which the moment of the force is 0. Exactly the same thing would happen if you tried to push a door towards its hinges. The moment exerted would be 0 and the door wouldn't rotate. So far, we've only looked at the rotational effect of a single force on an object. But what happens when two or more forces are present? Under the right conditions, these forces can combine to produce no overall turning effect on the object. When that happens, we say that the object satisfies something called the principle of moments, which says that when an object is in equilibrium, the sum of the anticlockwise moments about a pivot is equal to the sum of the clockwise moments. Writing this whole thing down in your exam could easily get you 2 or 3 marks. So it's well worth learning off. If you don't like this version, you can swap in equilibrium for balanced, sum of the anticlockwise moments for total anticlockwise moment, and likewise sum of the clockwise moments for total clockwise moment. Okay, so we know what the principle of moments says now, but what does it actually mean? Have a look at this girl and boy as they play on a seesaw. As you can see, the girl on the left is exerting an anti-clockwise moment about the pivot, and the boy on the right is exerting a clockwise moment. The anti-clockwise moment exerted by the girl is given by force times distance, which gives 450 times 2, which gives 900 Newton meters. Moving on, the clockwise moment exerted about the pivot by the boy's weight is given by 600 times 1.5, which gives 900 Newton meters. What we can see here is that the total anti-clockwise moment about the pivot is equal to the total clockwise moment. Together, they cancel one another out, and the seesaw will be in equilibrium. What happens though if the boy suddenly decides to move closer to the centre of the seesaw? By doing so, he decreases the perpendicular distance between the line of action of his weight and the pivot, and the clockwise moment he exerts decreases to 600 Newton meters. Because the anti-clockwise moment exerted by the girl is now greater than the clockwise moment exerted by the boy, the principle of moments no longer applies here, and the seesaw will rotate anti-clockwise. Let's try another example now. Here, we know that for the seesaw to be balanced, the total anti-clockwise moment about the pivot must be equal to the total clockwise moment. From the information given, we can only work out the clockwise moment which is exerted by the boy, so that works out to be 600 times 1.2, which gives 720 Newton meters. Let's use the same equation now for the girl's anti-clockwise moment. We know that for the seesaw to balance, it must have a value of 720 Newton meters, and that's equal here to 450 times d, which is the distance we're looking for. Rearranging then, d is 720 divided by 450, which gives an answer of 1.6 meters. Now that we know what moments are, we can go on to talk about levers and gears. Both devices, which are actually types of simple machines, are designed to make our lives easier. In some cases, they allow us to increase the size or turning effect of a force, and in others, they allow us to cause objects to move more quickly. Take a look at this rock. Looks pretty heavy, doesn't it? You probably could try and lift it, but you don't want to break your back, and to make matters worse, it would completely ruin your favourite jeans. There must be a better way. Indeed there is, my friends, and it involves some physics. A lever allows for the rotational effects of a force to be transmitted from one object to another. In this diagram, this is the lever, this is the pivot about which it rotates, and the rock is the load. Using the lever, the man applies a force here, which causes the lever to rotate, which in turn exerts a larger force on the rock, hopefully one that's large enough to lift it, saving your beloved back and your cherished jeans. Have a look at this example to see how this works. As you can see, we've been asked to work out the weight of the rock, which is going to be equal to the value of this upwards force F. When the farmer pushes downwards, we know that the clockwise moment exerted on the rock is going to be equal to the clockwise moment which he exerts about the pivot. Mathematically then, we can say that F times 0.7 equals 400 times 1.5, so then 0.7F is equal to 600, and dividing 600 by 0.7, F is equal to 857 newtons. That means that this is also the weight of the rock, which is 860 newtons to two significant figures. If the value of F is smaller than this, then the rock will stay put. If F is exactly equal to this, then the rock will be in the point of lifting, and for values of F larger than this, by even just a fraction of a newton, there'll be an upwards resultant force acting on the rock which causes it to rise. Levers come in all shapes and sizes, and we can actually split them into 3 different categories, but you don't need to know about these for your exam. Moving on. Gears are an essential component in lots of machines in which we want to transmit the rotational effects of a force from one place to another, be it in a car, bicycle, analog clock, or wind turbine. Gears allow for the rotational effects of a force to be increased or decreased. Here, when the input gear rotates clockwise, it causes the output gear to rotate anti-clockwise. By Newton's third law, when the input gear exerts a force on the output gear will exert an equal and opposite force on the input gear. This particular setup allows us to increase the turning effect of the input force from m equals Fd. The moment of this force about the axle at the centre of the input gear is F times r. For the output gear, because the force is the same but the value of d has doubled, the moment has increased to F times 2r. In other words, doubling the radius, or the number of teeth, between the input and output gears has doubled the moment or turning effect of the input force. Decreasing the radius of the output gear would have had the opposite effect here. One last example now to finish off. For part A, we can see that the force is 200 newtons and the perpendicular distance between the line of action of this force and the pivot, which is at the centre of the gear, is 0.1 meters. So that means that the moment is just 200 times 0.1, which gives 20 newton meters. Have a look at parts B and C now. For part B, from Newton's third law, the answer is the same as the force which appeared on the last screen, which is 200 newtons. For part C, the value of D for the rear gear wheel has decreased to 5 centimeters, so the answer is 200 times 0.05, just again they're converting to meters, which gives 10 newton meters. If the cyclist was to suddenly hit a hill, they could make their life easier by switching the rear gear to a cog with a larger radius or more teeth. This would increase the turning effect of their input force at the rear wheel, but unfortunately it would also decrease the speed at which the wheel is driven. That brings us to the end of this video. It's sad to lever you after such a variety of great video moments, but fear not. You'll be properly geared up for your exams once you've had a go at a few of the exam style questions. Good luck.